All right, so we are moving on to our final section in Unit 7, dealing with our inferences of mean data. And this last section is mostly just a summary of everything that we've gone over before. You should have a little fill out, a little sheet that we're going to go through, and we are going to fill out everything. And this kind of just summarizes everything for you. So you have it all kind of in one place, telling the difference between your proportions and your means of your one sample and two sample examples. Okay, so this kind of has everything all together when we're looking at our inferences of these. All right, so the first thing that we have here is just a flow chart, and you can look and see what you are trying to do, which test you should use. So what's your inference about? So is it about means or proportions, or is it talking about a relationship between two things? Those are with your chi-squareds or your regressions, which we talk about in the next sections. So your means proportions are kind of the two things. Mean is from your is from this unit, so unit 7, while the proportion was mostly in unit 6. And then from there, are you looking at one sample paired, two samples, one sample paired, several samples, etc. So there's a bunch of different ways from there, telling you if it's a T or a Z, T or a Z, T or a Z, etc., etc. So has everything. So for means, most part, it's probably going to be a T. Sometimes it's a Z if it's large enough. And for proportions, it's always a Z. Okay, so this is just a flow chart, so you can see, okay, this is what I'm trying to do, this is what I'm trying to find. Okay, so we will continue. Okay, so looking at your confidence intervals for means, and so the one sample Z interval proportions. So what you have there for each one of these, so when you fill them in, these are your formulas for each one. So the first one is with a proportion. Remember, you're using P, and you're using your standard error is the square root of P hat times 1 minus P hat all over N. Remember that the P is in decimal form. So it's not a percentage, it is a decimal. So 75% would be 0.75. The second one over here is talking about means with a Z. So you see you have your Z star there, so your Z critical. And then this last one you see is with a T. Exact same formula, it's just that standard error is what changes in each one depending on what the problem is. Okay, so if you have to use a Z, which remember is if you have your if you're more than 30 on your sample size, while your T is if you're under 30, and you're going to be using a T. So that's where a T is most common. Point estimates, which are your centers, okay, and that is again your P hat and your X bar. So that's the sample average. Okay, so it's the average or the mean that was found for each of these samples. Okay, so moving on to your X or your Z star and your T star. Okay, so again, Z is for a normal distribution. T is if you have a change in something. You're looking at your tail probabilities for both of them, and just remember with your T. You have a degree of freedom, which is going to be your n minus 1. So whatever your n minus 1 is, that's your degree of freedom, and you're looking at table B on those, while the Z is looking at table A. And depending on what it is, and that's assuming that your degree of freedom is off into infinity, assuming that's the populations. To find what your Z star is, you can use the inverse norm for your Z to find the tail, or inverse norm of the probability you want in one tail, and that's going to tell you what your Z value is. You can do the same with the inverse of a T, okay, under the same test area, and you do the tail probability, and then you have to also state what the degree of freedom is, okay, because remember the degree of freedom changes for those. Proportions, you always use a Z, and for the means, you use a Z if you have sigma, and you use a T if you have the sample. Okay, so if you have the sample, you use a T, sample deviation. If you have the population deviation, you use the Z. Okay, confidence intervals on a calculator. So using those, so one sample, you use one prop z int, and then the numbers that you plug in, x is the successes, n is the sample size, and then c is your level. If you are using your one sample z for means, that's z interval. So it depends on if you're using your data or your input. So if you're using data, then that means you are plugging numbers into your lists. So either L1, L2, whatever it is, and then you can go from there, plugging in what the deviation is and what the list you're using. The frequency should be 1, and then the C level. And then if you're just using the stats, then you're giving those numbers. So you're saying what the deviation is, you're saying what the mean is, you're saying what the n is, etc. And the last one is the T, which is very similar, but you use your T stuff. Okay. All right, so moving on from there, let's look at significant tests. So we were looking at intervals, now we're looking at significant tests with these. So looking with each one of these, remember that your null hypothesis is always going to be equal to. So no matter what it is, your null hypothesis should be equal to. If you're dealing with proportions, it's going to be P is equal to whatever the P0 is, so whatever that number is. So that P0 and mu0, those are going to be actual numbers. It's going to be equal to 0.6, going to be equal to 7, whatever it is. And then your alternative is where you're going to say if it's greater than or less than, okay? And that's your hypothesis, that's in your state. You also want to mention what your value is, or what the variable represents in this case. Next up is the conditions. And so the conditions for these, your random, independent, and normal. So random for all three of them is going to be either random sampling, SRS, or random assignment. The independence is also the same for all three. No matter what they are, you need your 10% or being told that they are independent trials. Okay, so the 10% condition. And then for the normal, remember proportions is where you use NP, and n times 1 minus p has to be greater than 10. While for normal, you're using more than 30. If it is more than 30, you use CLT, the central limit theorem. If it's less than 30, you can either use that the population is told to be normal, so the sample will be normal, or you could graph the data and then look at that and see is it normal. So, and again, if none of those hit, you just say proceed with caution, but you continue on. Okay, under do, so your formulas. So for each one of these, you want to make sure you draw your image. Okay, so you draw your bell curve and you want to show where the tail is on which side. Okay, the above are your formulas, which again are fairly straightforward. Make sure you shade on your value. It doesn't have to be perfect. And then the very bottom one is showing what your to find your p-values. So normal CDF is going to find your p-value for proportions and your z, while TCDF is going to find it for your t. Okay. And then your conclusion, if the p-value is less than alpha, you're going to reject in favor for HA. And then you use, we have convincing evidence of the alternative. And if it's the other way, then you fail to reject. So if the p-value is bigger than the alpha. And then you would just say that we do not have enough convincing evidence to say that it is. But we do not want to say that the null is correct. We don't want to say we've proven the null hypothesis. Okay, that is bad. All right. Now the rest of it is just kind of a summary of that sheet, so you can kind of look through and see it. Make sure you never pool data. Okay, data should never be pooled for anything. All right. And that's it. That's the end of 7. Moving on to 8.